next talk so that we can try to keep to time. So thanks very much, Lana, and indeed, if you have further questions after the talk, please do ask them in the Slack channel. And now it's time for the next talk in this session, which is by Ophelia Crawford. Hopefully Ophelia is also on the line now. And this talk is going to be about efficient quantum measurement of Pauli operators in the presence of finite sampling error. So I'll just hand over to Ophelia now for her talk. Thank you.
Yeah, great. Thank you very much, Ashley. And yeah, so this talk is focused on reducing the resources required in order to make measurements of Pauli operators. And again, as in Lana's talk, the main application we're focused on is computational chemistry calculations using the variational quantum eigensolver. So when we're performing these types of calculations, what we're interested in is finding the ground state energy of molecular or solid state systems. And this corresponds to finding the lowest eigenvalue of a Hamiltonian. The variational quantum eigensolver is one such way of doing this. And as Lana said, it's a hybrid algorithm. So it uses both the classical computer and the quantum computer to perform the bits that the classical computer finds hard. And the way the algorithm works is using some parameterized circuit. A classical optimizer seeks to optimize over the expectation of some parameterized quantum state with the Hamiltonian. So looking at this sort of schematic flowchart on the right, the classical computer chooses some parameters lambda. The quantum computer prepares the state corresponding to those parameters, makes some measurements upon them, and typically this will have to be repeated, this state preparation and measurement step, and then evaluates the expectation of the Hamiltonian using those measurements, hoping to find the overall minimum. And if we've chosen our ansatz correctly, and if the classical optimizer has performed well, then we hope what we return is close to the true ground state of the Hamiltonian. So in this talk, I'm going to be focusing on these two boxes here in particular. So what measurements we need to make of the quantum state, and then how we use those measurements to obtain this expectation of the Hamiltonian, and looking to try and make this process as efficient as possible, so use as few resources on the quantum computer as we can. So when we're making an expectation of the Hamiltonian, we typically can't make measurements of the Hamiltonian directly. And so instead, we write the Hamiltonian as some sum of Pauli operators, of which we can make measurements directly. And this Hamiltonian is then weighted with some coefficients, AI, on the Pauli operators, Pi. The expectation of the Hamiltonian on a particular quantum state is then given by the sum over the coefficients with the expectations on the particular Paulis. So for example, if one of our Pauli operators is x on qubit 1 and y on qubit 2, on the quantum computer, we will prepare the quantum state corresponding to a particular value of the parameter, then measure x on qubit 1 and y on qubit 2, get a measurement of x1, y2. In order to obtain the expectation, we need many measurements of a particular Pauli. So this circuit will be repeated many times, and then we'll repeat it for all the Paulis. However, quantum mechanically, we know that if Pauli operators commute, we're able to obtain measurements of them at the same time. But it's not immediately clear how we could do that from this circuit. So we necessarily have a measurement of x on qubit 1 and y on qubit 2. And so we're not able to obtain a measurement of some other commuting operator that doesn't involve those operators. However, if we can do so, and if we can then collect the terms in our Hamiltonian into sort of commuting collections, we might, as this sort of schematic here illustrates, be able to reduce the number of circuits we need to run. So say we have a collection of 16 commuting operators. In traditional methods, in order to obtain a measurement of each of them, we'd have to run each circuit once to obtain a measurement of each. But instead, if we can find a way to obtain a measurement of all of them simultaneously, we can then just run a single circuit and get a measurement of all 16. And it's this idea that this talk is focused on. In order to use such a method, there are sort of two questions we need to answer. So one is, given the operators, the Pauli operators in the Hamiltonian, how can we best collect them into commuting collections, as there'll be many different ways in general that we can do this. And then the second question is, once we have the operators in a particular collection, how do we actually obtain a measurement of all of them simultaneously? So in general, we'll need to add an additional part to the circuit that I've labeled Q in this diagram here. So to begin with, I'm going to focus on how we collect the operators together. And one thought that might immediately spring to mind is that we should try to collect them into as few different groups as possible. However, I'll demonstrate that this isn't necessarily the best thing to do and doesn't necessarily lead to the best savings. And in fact, we propose a different method. So first of all, I'd just like to talk about how many measurements we need of each Pauli operator in order to obtain an expectation of the Hamiltonian to within a certain degree of accuracy. So following these papers at the bottom here, we can use Lagrange multipliers to optimize over the number of measurements for a fixed error. So we'd like to get to a certain level of error with as few measurements as possible. And what we find when we do this is that the number of measurements we should make of a particular Pauli operator depends on both the Pauli operator's coefficient AI and also on the expectation of the Pauli operator on the quantum state through the variance pi. And so, yeah, the conclusion, the key points here are that each Pauli is measured a different number of times, and it depends on both the coefficient and the expectation. And we can then also calculate the total number of measurements required in order to obtain an expectation of the Hamiltonian. And if we repeat this analysis for if we've collected the Paulis into commuting groups, this gives us a kind of natural metric for how well a particular way of collecting operators together performs. So we've called this R, and it's simply the ratio of the number of measurements in the uncollected case. So if we measure all the Paulis separately to the number of measurements in the collected case. So once we've grouped them together into commuting collections. So for example, if we require half as many measurements in the collected case, that gives us an R value of 2. However, as I've said, these numbers of measurements depend not only on the coefficients, but also on the expectations of the Paulis with respect to a particular quantum state. And we don't know these things a priori. And so we instead propose a slightly different metric, R hat, which is taking the R metric and averaging over all the expectations, taking the R average over the expectations. And so this gives us a metric that just depends on the coefficients in the Hamiltonian, which we have access to a priori. So when I'm discussing different methods for collecting operators together, I'm going to be talking about it in the context of wanting to maximize this R hat metric. So considering just a simple example to kind of try and illustrate the idea behind our methods, I've here given a very simple Hamiltonian. It's just got 4 terms and it's defined on 2 qubits. And there's one way of collecting the terms into just 2 collections shown on the left here, and this gives us an R hat value of 1.47. However, if we in fact collect them into 3 collections, as shown on the right here, this gives us a higher R hat value, an R hat value of 1.71. And so considering examples like this leads us to suggest our method for collecting terms together, which we've called sorted insertion. And the way this works is that each operator in the Hamiltonian is sorted by the magnitude of its coefficients. Then each operator is taken in turn, inserted into an existing collection if it can be, and if not, a new collection is started. And application of this method gives the 3 collections here that gives the R hat value of 1.71. So extending this now to some real Hamiltonians for real molecular systems gives this quite dense table here. So the key points is what I'm showing on the left is for different molecules. So these will require different numbers of qubits. I'm showing the performance of our method, sorted insertion, in this right-hand column here, against several different methods that are seeking to find the smallest number of collections, so the minimum clique cover. And in each row, I've highlighted the largest value of R hat. So this is the method that gives the greatest savings. And what we can see is that in nearly every case, sorted insertion has the highest R hat value. And just extending this then to some slightly larger systems, we can see that although there's quite a range in the speed up for different numbers of qubits, so speed up here is the R hat value, we can see it's broadly increasing with system size, and the savings over traditional VQE go up to a factor of about 65. So I'm now going to turn my attention to the other aspect of the problem, which is, given a particular collection of commuting operators, how can we actually obtain a measurement of each of them? And in this area, we contribute 2 methods for circuit construction. So one we've called CZ construction and one we've called C0 construction. And the key thing we've tried to do here is minimize the number of 2-qubit gates, as these are typically the most quantum computationally intensive resource, either because of the time they take to run or because of the errors associated with them. And what these methods have in common is that they take advantage of the rank of a particular collection of operators. So this is the number of independent operators in a collection. So for example, if we had the operators x1, x2, and x1, x2, although there are 3 operators, the rank is only 2 because the third operator is a product of the other 2. And we also use classical post-processing in order to take the products of measurements. So I'm just going to talk a little bit more about our CZ construction, but our paper about this also contains more details of both of them. And in order to create these constructions, we've made use of the binary framework for representing Pauli operators. And this is just a way of writing and manipulating Pauli operators in matrices. So using matrices consisting of 0s and 1s. And we're able to collect together Pauli strings of different lengths and have multiple Pauli strings as different columns in this matrix. And then 1 and 2 qubit gates can be applied by manipulating the relevant rows of the matrix. And for this CZ construction, we make use of a particular type of Pauli operators known as graph states. So these Pauli operators have X's kind of on their diagonals and then Z's on the off diagonals. And the reason they're called graph states is that these can be made into diagonal operators, so things that we can measure simply on a quantum computer, just by applying control Z's between the nodes on this graph that have an edge, and these correspond to the off diagonal Z's here. And a graph state looks like the identity in the bottom half of the binary matrix and a symmetric matrix in the top half of the binary matrix. And this paper we make use of says that any collection of n independent n qubit commuting Paulis can be transformed to a graph state using 1 qubit rotations and classical post-processing only. So we extend this to the reduced rank case in order to construct our circuit. And just to illustrate this with an example, so I'm taking 3 Pauli operators here, and I would like to be able to obtain measurements of all of them at the same time, just from 1 state preparation. What we can see is that actually only 2 of these operators are independent. The third one is just the product of the other 2. And so we take these 2 and write them in the binary matrix. We then make use of this paper to manipulate them into this form here using just 1 qubit gates and classical post-processing. And we'd like to get them into a graph state, as then we know we just need additional control Z gates. But in order to do so, we need an identity in this bottom half here, which currently we can't do because it's not a square matrix. So what we did in our paper is to add 2 additional columns of Pauli's constructed in such a way that we don't, that we minimize the total number of 2-qubit gates. So having done this construction, we then follow the methods in this paper again and manipulate the total operators into a graph state. But the key thing here is these zeros that I've highlighted with the blue square. And the way we constructed our additional operators mean these are necessarily zeros. And so that limits our control Z gate count. So I've said we want to minimize the 2-qubit gates. And this graph here is just showing the maximum number of 2-qubit gates for our explicit examples divided by the number of qubits squared. So what we can see is that it's at a maximum about a 6th times the number of qubits squared, number of additional 2-qubit gates, which is probably going to be far less than the number required to prepare the state. So I'll just leave you with the slide showing our speed up, the value of R hat for the different number of qubits, and conclude by saying, so I've presented today a method for reducing the quantum computational resources required to obtain an expectation of a Hamiltonian by grouping together collections of commuting Pauli operators and constructing a circuit to enable measurement of them all simultaneously. Thanks very much.
Fantastic. Thank you very much, Ophelia, for that great talk. So just like the last talk, while people have a chance to get typing and ask some questions on Slack, I'll start out by asking a question of my own. So I'm not 100% sure it's a question that makes sense, but you mentioned these different strategies for this grouping, and I noticed one of them is this algorithm DSATA, which is a greedy coloring algorithm, I guess. So I was just wondering, I mean, does it make sense to think about non-greedy coloring algorithms? Because, you know, there are algorithms which are designed for coloring graphs and which might run in exponential time, but maybe for a graph of a size that you're sort of looking at, it won't be completely infeasible. So I don't know if that's something that makes sense.
Yeah, so in this table here, we do show, so there are sort of the first 4 columns are all methods that are seeking to find the smallest number of groups. So yeah, they work in different ways. I don't think any of them are none of them are exponential time ones. But I guess it's reasonably consistent that the sort of smallest numbers of groups typically lead to nowhere close to the best solution. So say, for example, in the N2 row, the independent set manages to group into just 39, but it has a much, much lower value of R hat despite that. So yeah, I guess I'd say I don't know if any of these are necessarily finding the actual smallest number of groups, but I would be inclined to say that even if they did, that probably won't be the best thing to do. Yeah, that it suggests that our sort of sorted insertion that's based on actually the coefficients in the Hamiltonian does seem to lead to better results.
Fantastic, thank you. So just to go through some of these questions that people are posting on Slack. So the first one is by, sorry if I'm pronouncing this wrongly, Xavi Bonnet, who's asking, what's the classical cost of the Pauli grouping algorithm that you're using?
Yeah, that's a good question. So we firstly sort the terms in order of descending coefficient. So I guess you can do that in number of terms. If the number of terms is m, you can do that in m log m, although quite possibly, given the way you calculate the Hamiltonian from sort of the 1 and 2 electron integrals anyway, you might be able to construct it in a way such that you get them ordered to begin with. And then it's just a case of taking each term, comparing it with all the ones already in a collection to see if it commutes with everything in a particular collection, and then if not, putting it in a new one. So that's going to require at a maximum half m squared comparisons. So at a maximum comparing each Pauli with every other. So yeah, order m squared, where m is the number of terms in the Hamiltonian.
Thank you. Now there's a question, well, I'm going to perhaps summarize a question that several people have asked in different ways. So it's this question by Michael Castoriano, Ross Duncan, and also Elliot Ball. So basically their question is, roughly speaking, Michael's question is, do we have a comparison of R and R hat for small systems? And the other two, I guess, we're asking, how well does R hat approximate R for some really real examples?
Yeah, that's a really good question. So we found, so in our paper, we do show explicit calculations of R for some small systems, just for a particular ansatz, in order to, a particular ansatz choosing, I think we did 100 random parameters on this particular ansatz. And what we did find was that R hat does pretty closely approximate this average of R. I think in practice, what you'd want to do is try this for whatever ansatz you're using as well, to see how well it approximates it in that case. But yeah, we did find on the systems we considered, we did find R hat was a pretty good approximator for the average of R. And yeah, there's data for that in the paper as well.
Fantastic. So I think I might just ask one more question for now, as we're sort of heading towards the break, and then perhaps any further ones can be discussed on Slack. So it's a question from Adrian Perez Salinas, who's saying that the tools used for the construction of Q remind him of the quantum error correcting codes, and he's asking if there's a relation between the topics, and perhaps if you can use techniques from quantum error correction here.
Yeah, I guess so. I personally don't know a huge amount about quantum error correction. Yeah, I mean, certainly, I guess my understanding would be when we find out the sort of independent terms in a particular collection, that does kind of correspond to a stabilizer, and then we're looking to map that in the control Z construction to a graph state, which I guess is a particular type of that. So yeah, so in these two papers, it is just all about, so in the C01, say simulation of stabilizer circuits. So yeah, it's about using as small a circuit as possible in order to diagonalize a set of Paulis. So I would guess, yeah, you can. Yeah.
Great. Okay. So I think that now is just about time to go to the break. So thank you very much to both of the speakers for some fantastic talks to kick things off. So I just want to mention as well that we have a poster session starting at 11, though, I guess, it can start whenever people want it to start, really. And this is happening on Slack, and this is an opportunity for people to post their posters and to discuss them as well. Which in many ways, I guess, is superior to a traditional physical poster session, because it's much easier to see many posters in one go and discuss them with the authors. So please do take advantage of that and discuss the posters, because I know there are a lot of fantastic posters at this year's conference. And we're going to be restarting the next sort of session at 11:10, which is the time for the hardware panel discussion. So we're going to have a hardware panel discussion and then another contributed talk. So thank you very much for tuning in so far. It's fantastic to see almost 200 people at this very first session, and we're going to be restarting at 11:10 for the hardware panel. Thanks very much.